Note that we can extend Fermat's little theorem for non-primes as well. We just have to be a little bit more careful. What Fermat's little theorem said was a to the power p minus 1 mod p is 1 if p is a prime. For non-primes, it turns out the theorem we have is a to the power 5n mod n is equal to 1, where 5n is the number of numbers that are relatively prime to n. Now that's a little bit too much to grasp, so I want to focus on an example. But before I do that, I want to also remind you that when we do that, I want a and n to be relatively prime. So recall what phi n is. It is the number of numbers less than n such that GCD of x and n is 1. So if n is a prime, then every number less than n is relatively prime to n. Therefore, when I'm computing phi of n, essentially I'm going to have the set 1, 2, all the way up to n minus 1. And therefore, the number of such numbers is n minus 1. And that's exactly the original Fermat's little theorem. If I were to compute phi of 15, I need to look at all numbers from 1 through 14 which are relatively prime to 15. And in that case, those numbers are going to be 1, 2, 4, 7, 8, 11, 13, 14. Note that numbers like 6 is not there because GCD of 6 and 15 is not 1. This means that we can conclude that 4 to the power 8 mod 15 is 1. 7 to the power 8 mod 15 is 1, and so on. Note that 6 to the power 8 mod 15 is not 1 because 6 and 15 are not relatively prime. I would like to add one note. Finding phi of n is not always easy. It is easy if n is prime because it's n minus 1. It's easy if it's a product of two primes, like 3 times pi 15, 7 times 321, 7 times 1177, then it's easy. Otherwise, it is not always easy. In general, you need to know factorization of n to find phi of n. And it turns out that factorization is a difficult problem when the numbers are large. We have reached the check before you go ahead slide. I would like you to be able to answer which of these statements will be true, if or rather what will be the value of x that will make these statements true.